Well, good evening, AP Physics students. New topic for us tonight. We're going to talk a little geometric optics tonight. Think about mirrors and lenses and all that good type of thing. So, these things called mirrors and lenses, how do they work? And what is going on with them? Well, let's just introduce a little terminology here. So, you may have been told in your life that you were a ray of sunshine, right? Well, what is a ray of light? Well, it's just a narrow beam of light. And off any object, there's thousands of rays of light bouncing off of them. But we're usually only interested in a few of those rays of light because those few rays of light can tell us what's going on with the rest of the light. So for instance, here I have a plain mirror, just a regular flat mirror like maybe you have in your bathroom or something like that. And here I've drawn a ray of light and it's reflecting off of the plain mirror. And the angle here at which it is coming into the mirror we call the angle of incidence. And it's always measured from the normal. So here's the ray of light, here's a perpendicular or normal. And the theta sub I is called the angle of incidence, the angle at which the light is coming in and hitting the mirror. And then for a flat plane mirror, the angle of incidence is equal to the angle of reflection. So the light bounces in, comes in at the same angle that it goes out, which kind of makes sense. All right? So those are some basics about mirrors. Now, when you look at a mirror, you might be standing a certain distance away from a mirror. The distance you are away from a mirror is called the object distance. And maybe it's not you, it's whatever you're looking at in the mirror. So the actual distance the object is from the mirror, we call that the object distance. The distance where the image appears to be is referred to as the image distance. And I was going to try to draw this out, and it just didn't work that well. So let's take a little picture here from the book. So here I'm looking at an object in a mirror. D sub O here is the actual object distance. And the distance the image that you see appears behind the mirror we call the image distance. Okay? So, a little bit of vocabulary there. We have a image distance and an object distance. Now, a little bit more terminology here. Let's talk about virtual images and real images. Let's cover that up for another minute here. So, a virtual image is an image that would not appear on a piece of paper, piece of white paper placed at the image distance. Whereas a real image, the image would appear on a piece of paper. In other words, let's see here. If I stood behind this mirror and held up a piece of paper right here, no light would actually be shining on that paper, right? It might be kind of dark behind the mirror. Therefore, this is a virtual image, right? So a lot of times with mirrors, you might be seeing, well, I won't generalize, but a virtual image is one where if you held a piece of paper where the image actually is, no light would actually be touching it. Now that's different from a real image, right? So no actual light at the image and actual light at the image. Now, if all of our mirrors were just flat, wouldn't life be boring, right? So we have invented convex mirrors and concave mirrors. You might have a convex mirror on your side rear view mirror on your car. And they let you see kind of a greater area reflecting in them. Concave mirrors are also popular. Sometimes, you might use a concave mirror if you want to heat something up. I've seen solar cookers that heat things just by the heat of the sun that are basically giant concave mirrors, right? So here the light's being reflected in the concave mirror. Here the light is being reflected out. Now, here is what we call a ray diagram. Okay, so I have a mirror here. In this case, this is a concave mirror, and images look different in concave mirrors. If you've ever been to like a fun house or house of mirrors, you know that you look different in concave or convex mirrors. So to figure out, predict what things might look like, we draw what we call ray diagrams. And that is, we just draw different rays of light coming in and bouncing off of our curved mirror in different ways. A little bit of terminology here. If I draw a center line down the middle of a mirror here, just an imaginary line, we call that the principal axis. So just an imaginary line splitting the mirror in half there. This F point here is called the focus. All right, and if light comes in parallel and bounces off the mirror, the light will go through the focus. And then C here is called the center of curvature. And we sometimes put R, you'll see an R instead of a C for that, because this is actually the radius of the spherical section of the mirror. So if this were a full circle, this would be the center of the circle. So we call this the center of curvature, and we call F the focus. So far, lots of terminology here, but why don't we get to a little bit of problem solving here? Okay, so some problem solving here. So one way to predict where an image might form is to use what we call a ray diagram. Okay, so if I have an object and I place it in front of a mirror, okay, I can draw 3 rays and use those rays to predict where the object would appear. The F ray goes through the focus. The P ray starts out parallel and ends up going through the focus. And the C ray bounces right off the mirror and goes right back through the center. Now, I tried to draw this and did not do a very good job of it. So I'm going to refer you to some really good pictures in your book here that are actually to scale. So here I see a parallel ray. So here's my object, and this ray of light is bouncing off the mirror and going through the focus. Here I see a ray of light going through the focus and bouncing off the mirror. And here I see a C ray. That is one that bounces off the center, bounces off the mirror and goes right through the center. And where these rays converge is where the eye would actually see the image. So here's where the object is, and here's where the image would be. So since there is actual light going through this image, this would be a real image. Okay? Okay. So, ray diagrams are something you have to practice a little bit, but a way you can double check your work on ray diagrams is with the mirror equation, okay? And the mirror equation states that if I put 1 over the focal length over here, that is equal to 1 over the object length plus 1 over the image length. All right, so this is a good algebra way of checking if you've done your ray diagram to see if you can predict where the image of a certain mirror would be produced. So in problem number 8, we can use this equation to help solve our problem. In problem number 8, it states, hey, if I wanted the image distance to be off at infinity, where would I place the object if I had a mirror with a focal length of 23 centimeters? So here are some hints on how to solve that. The image distance way off at infinity would mean 1 over infinity, which is 0. Don't tell Mr. Meyering I said 1 over infinity is 0. So therefore, the object, we would want to place the object at the focus, okay? So solving for that, if the radius of curvature or center of the mirror is at 23 centimeters, the focus would be at half of that distance. So we would want to place the object at the focus, or 11.5 centimeters away from the mirror, in order to get the image to appear as if it's at infinity. Okay? All right, nice work, AP Physics students. Man, that's a lot of information, Mr. Kirsten. What in the world could this stuff ever be used for? All these images and mirrors and all that kind of stuff. Well, I don't know. Maybe for discovering new planets with, telescopes like the NASA's Kepler Space Telescope, which just discovered some planets in a star 1,200 light years away that may be very Earth-like, may support life. They are in the Goldilocks zone, meaning they're not too hot and they're not too cold. They're just the perfect Katy Perry-like temperature where maybe these planets might support life. So these newest planets called Kepler-62 and Kepler-62e might just be glimpses at other worlds with intelligent life on them. All possible because some young scientists learned how to manipulate telescopes and images and objects and lights and knew their ray diagrams and all that good kind of stuff. So it really is a brave new world out there in planetary exploration. All right, nice work, AP Physics students. We'll see you tomorrow.